Hey there, everybody. Welcome back. This is 14.7 in Calculus 3. We're using the Anton 11th edition book. This is on changing variables and multiple integrals, and this develops the Jacobian. Think U sub, but at a higher level, multi-dimensional. Okay? And in fact, speaking of U sub, recall what we did with U subs. We'd start off with f of x dx. We'd replace x with some function of u. Then we take the derivative and find our dx in terms of du, and we replace it. So like if we had x squared, and we had 2x, and we'd have 2x dx equals du, so and we'd end up with maybe 1/2. We divided by 2. We did this a lot recently. We only, like when we did RDR, if we had r squared, inside and plus something like that, and we had an r outside, we do u equals r squared plus 1, du equals 2r dr, and 1/2 du equals r dr. This is the 1/2. Well, really, it's 1/2r du equals dr. So let's say that was a dr. And we're placing it back in, so we've got square root of u times 1/2r du. We still have the r in front. The r cancels, and we got 1/2 square root of u du. So that's how we did it before. Let's upgrade this to multi-dimensions. And so let's take a look how this works. Let's say x, and we've got x and y, and now these are both functions and not just u, but u and v. So we can make a vector where r is going to guv for the I hat component, that's our x value, and then h of u and v for our y value, our j component. And if we think of u and v as an input into the two functions, with x and y as the output, then these two equations define a function t that transforms points in the uv plane into points in the xy plane. And we could do something going in reverse, going the other direction, transferring xy into the uv plane. So let's just define a transformation t, where the transformation t of u and v, it was x and y, but now we're doing it replacing with every x and y is replaced with u and v. So we're kind of like taking stuff in our set S over here, and our set R where xy is, we're mapping it over to uv. Mapping is a word that we're going to be using. Maps. And like they use the terminology like R is the image of S under the transformation, and vice versa. So if we have some set R and it's all points x, y, and we map it by t from the uv points in S, then it's called the image of set S under t. A lot of terminology. I'm not gonna. If you want to go into mathematics, you will, and you'll do more of this later on. You do a lot of stuff with mapping and imaging and stuff like that. But one way of looking at it is we could have constant curve lines, well, constant curves. They may be straight lines in the UV plane, but when we map them over to X and Y, they're crappy looking. And going vice versa, we map the other direction. We can map XY, crappy XY stuff over into nice straight UV lines. Wouldn't that be fun? We got some image like this in our XY plane. Look at that crappy integrand. Weird lines, stuff like that, but then it maps over to something as simple as this, a rectangle. So this is the motive behind it. If each point in the set comes from only one point in the other set, it's called a one-to-one transformation, and it has an inverse. So we can write u as functions of x, y, v as functions of x, y, and then x as functions of u and v, and y as functions of u and v. Let's just look at some examples. This is kind of math jargony. If you like it, you like it. If you don't, if you're here for engineering, like most Calc 3 students are, jargony. Let's go look at some videos in the next, or examples in the next videos. Peace.